All right, we're back. This is going to be page 8 of notes 14 of Calc C. We were doing logistic differential equation. I think we've mastered that concept, hopefully. And now we're just going to do some review problems that are about series. So let's take a look. The function f has derivatives of all orders, and the Maclaurin series for g of x is given by this. I don't know what f has to do with this, like at all. There's no f in this problem at all. I wonder if that f is supposed to be a g. Probably. I'm thinking this is supposed to be the function g has derivatives of all orders. Maybe. All right. Determine the interval of convergence for the Maclaurin series. All right. So interval of convergence. We got to do the ratio test. So it's the absolute value -1 to the n plus 2, which you don't really need to worry about because the absolute value is just going to like kill that. When you plug in n plus 1 to 3n, you get 3n plus 3 and then minus 2. So 3n plus 1 over. When you plug in n plus 1 to 2n, you get 2n plus 2 and then plus 5. So 2n plus 7 multiplied by the reciprocal, 2n plus 5 over -1 to the n plus 1, which again, we don't need to worry about because, absolute values. And then x to the 3n minus 2. Oh, we're going to get like a cube, I think. So when we if you take the limit, you end up with, these are going to, here, let's highlight. Like this and this, the absolute value kill, so it doesn't really matter. If you're going to infinity, then the ratio of this and this goes to 1. So you end up with, what do you end up with? 3n plus 1. So it's x to the 3n, x to the a over x to the b is x to the a minus b. So you have 3n plus 1 minus 3n minus 2. That's 3n plus 1 minus 3n plus 2. You get x cubed. So this is the absolute value of x cubed. So this will converge when the absolute value, so converges for the absolute value of x cubed less than 1, which just means the absolute value of x is less than 1, which is good. So we need the absolute value of x to be less than 1. That's the open interval. So the radius of convergence is 1. That's the open interval on which this thing converges absolutely. Now we test the endpoint. So let's let x equal -1. And what we're doing is we go back up here and we replace x with -1 and see what kind of thing we get. So we'll have from 1, so we have -1 to the n plus 1 already, and then we'll have another -1 to the 3n minus 2. So it's going to come down to whether or not this actually alternates. Because if it alternates, it converges. If it doesn't alternate, it diverges. So this will be -1 to the n plus 1 plus 3n minus 2 is, there's 4n minus 1. 4n minus 1. 4n minus 1, if n is 1, you get 3. If n is 2, you get 7. If n is, oh, actually, this is always odd, so this does not alternate. 2n plus 5. So, this is really just -1 over 2n plus 5, which definitely diverges. And you could limit compare to 1 over n, or -1 over n, I guess, which is the harmonic, and that diverges. And then if we let x equal 1, what do we get? N equals 1. You have -1 to the n plus 1 over 2n plus 5. This converges by alternating series test. And you can apply the test if you want, but like at this point, usually you can just like say it. And so that's what I'm doing. I'm saying that it just does. So it doesn't converge. So interval of convergence. We're going to not converge at -1, but we do converge at 1. So I think we get that. Let's highlight that. So you got to do basically all that work to work this out. Not bad though. I don't know. Good problem. Good problem. Good review. The approximation for g of 1/2 using the first two non-zero terms. So what that says is if we go up here and plug in 1/2 everywhere we see an x, that'll give it, because this is g of x. So if we plug in 1/2 everywhere we see x, we would get, using just the first two terms, we'd have 1/2 over 7 minus 1/2 to the 4th over 9. Add those up and you get this apparently. What we want to do is show that this approximation differs by less than 1 over 1400. Okay, I have a thought. My thought is, if x is equal to 1/2, then you get a convergent. So x equals 1/2 is in the interval of convergence, which means that at x equals 1/2, it's actually an absolutely convergent series. So it definitely is a convergent alternating series. So here we go. I'm gonna start writing this and see how it goes. So I guess at x equals 1/2, the sum 1, -1 to the n plus 1, 1/2 to the, what was it, 3n minus 2 maybe? Yeah, 3n minus 2 over 2n plus 5, I think, because we got 2n plus 7. Yeah. Whew. Is a convergent alternating series. Therefore, the error is less than the magnitude of the first term left off. I'm going to say first term omitted because it sounds classier, but first term left off is the same. But then I got to spell omitted. That's almost certainly right, plus or minus a t and an m. But I think that's right. So therefore, the error is going to be less than. So the first term that we left off would be plugging 1/2 in here. Fantastic. So that's going to be 1 over 2 to the 7th, and then over 1, 2, 3. If I plug in 3 here, I get 6 plus over 11, which I think was actually up there. I don't know what that is. 2 to the 5th I know is 32. And I always have to like double and double. So 64, 128. So this is 1 over 11 times 128. And then if I had a calculator, I would just use it, but I don't think I do. So that's going to be 1280 and then 128. 1408. 1 over 1408, which is definitely less than, but not by much, 1400. So it works. It's super close though. Right, the first 3 non-zero terms and the general term of the Maclaurin series for G double prime. Crud. All right. So let's borrow the terms we were given. So we had x over 7 minus x to the 4th over 9. So this is g of x. It is x to the 7th, x over, I don't know, x to the 4th over 9. And then I think it's going to be x to the 7th, right? I'm just adding 3 and then adding 2 in the denominator. I got to keep going so that I have enough terms that when I take the derivative a couple times, it's going to like work. X to the 13th over 15 and plus dot 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 plus -1 to the n plus 1, because we got to take the derivative a bunch of times. X to the 3n, I don't remember, 3n minus 2 over 2n plus 5 plus dot dot dot. All right, let's differentiate. It's literally just a power rule like twice, so not a big deal, but man, does it mess people up. 1/7 minus 4x cubed over 9 plus 7x to the 6th over 11. So I need the first 3 non-zero terms. So if I do one more, then when I take the derivative again, we're going to knock that out, but we'll have 3 terms left over, so that's good. Also, don't stop in the middle of what you're doing to highlight things. I don't know who I'm yelling at, probably me. This can be hard to fit. 3n minus 2 x to the 3n minus 3 over 2n plus 5, which we've decided to put in parentheses now. One more time. All right, so g double prime of x is going to be negative 12x squared over 9. I don't see the point in simplifying that, so I'm not going to. Plus 42x to the 5th over 11 minus 90x to the 8th over 13 plus dot, dot, dot. So this is the one you really got to cram. You got negative 1 to the n plus 1. 3n minus 2, 3n minus 3, x to the 3n minus 4. I think we made it. 2n plus 5 plus dot, dot, dot. Whew, okay. Term by term is the way to go. You don't mess around with those summations when you're doing it term by term, which is what I really like about it. Gotta make sure not to pick up this highlighter because I'm going for the whole thing here. There we go. Look at that. All right. That's it. That's the review for this page. I'm going to come back in the next video and do more. And, you never want to be too far from the last time that you did series problems. So I'll be back in the next one and we'll take a look.